Hello, hello, hello. I'm gonna get straight to it. This is a really cool proof. It's a little bit of cheating, but not really. So, a lot of you guys are probably aware of one of the coolest equations in math. E to the I theta is cosine of theta plus I times the sine of theta. And the traditional way to go about proving that is to take the Taylor series for e to the x, which is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. The Taylor series for cosine of x, which is cosine is an even function. That's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. And we take the Taylor series for sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. And what you can do is you can plug in for x, you can have x become ix, and you'll actually get, if you plug into this Taylor series here, the two Taylor series for those. And that's the traditional way to go about it, but that takes towards the end of Calc 2 to actually prove. And a lot of times people are seeing this formula here in pre-calculus or in Calc 1. And so I'm going to present a way that you can, and it's kind of cheating, but it's not technically circular, to prove this formula without actually using any Taylor series. Just basic differentiation is all you need. The product rule and basic differentiation is all. So here it is. Let's consider f of theta to be e to the negative I theta times cosine of theta plus I times the sine of theta. And let's find f prime of theta. We have a product here, so we're going to use the product rule. So we got e to the negative I theta times the derivative of this, which is negative sine theta plus I times the cosine of theta, plus, it's actually going to be minus now, minus e to the minus I theta times cosine theta plus I sine theta. And we can distribute that out. That's minus e to the minus I theta sine theta plus I e to the negative I theta cosine theta minus whoopsies, I forgot the I here. See, I took the derivative here of the e to the negative I theta, which it becomes negative I e to the negative I theta minus I, there we go. Because we differentiate, the theta becomes just 1, and then I is a constant. So minus I e to the negative I theta times the cosine of theta. And this is going to be, we have a negative I squared, that's 1, so plus e to the negative I theta times the sine of theta. Now, this is really nice, right? This and this, gone. They're gone. They're the same. This and this are the same, they're gone. So this whole thing is just equal to 0. So what does that imply about f of theta? Well, if f prime of theta is 0, then the graph of f of theta has to be a constant, right? Because its rate of change is 0. It's not changing at all. So f of theta just has to be a constant. So we can say then, for all values of theta, that e to the negative I theta times cosine theta plus I times the sine of theta is equal to the same constant, which I'll just call k. And we can just solve for k by plugging in any value of theta we want. I'm going to choose a nice value and let theta be equal to 0. So e to the 0 is 1, so we have 1 times cosine of 0 is 1, plus sine of 0 is 0, so 1 is equal to k. So this implies e to the negative I theta times cosine theta, and you're probably already seeing it now, plus I sine theta, is equal to 1, and I can multiply both sides by e to the I theta, and I get cosine theta plus I sine theta is e to the I theta, Q, E, D, and we're done. That's really cool. Just one thing I kind of want to mention, just kind of behind the scenes, what actually happened in my mind here is, and this is why you might say it's circular. Technically, the way I've presented it, it's not circular. Now, how I actually came up with this function, well, I mean, I already knew the formula beforehand, so maybe that's the circular part, but technically it really isn't. So what I said to myself, I said, well, I know that this is true, and so I said, well, I'm going to multiply both sides by e to the negative I theta. And if I multiply both sides of this equation by e to the negative I theta, then I get this. I get this right here. And then I said, well, I know if I differentiate both sides that this derivative, for this function here, it's just going to be 0 because when I differentiate this side, it's 0. So and they both have to be equal to each other. So I said, well, I know these are going to be 0, and I can just solve for k. So that's kind of a cool tidbit proof I just wanted to share. Yeah, we're done.